Hey guys, welcome to this particular session. And in this video, I'm going to be talking about meta-analysis for beginners. This is actually that video for anybody who is interested in starting a meta-analysis. So regardless of your background, whether you've done a meta-analysis before, I'm going to keep everything simple in this session. And everything I'm going to be looking at is how you can actually get very solid with the theories, with the foundations of everything you need to know about performing a meta-analysis. Remember that the meta-analysis is rooted from a systematic review. So it means that you still need some kind of prior knowledge of how to conduct a systematic review before you can be able to get started with meta-analysis. If you like this video and you find it very interesting, why not hit the like button and share, subscribe, depending on the platform where you are watching or listening to this particular video. All right, so we're gonna jump into making things straight, and I'm going to talk about what's the meta-analysis in simple terms, then talk about some of the tools that you can use to get started, and effect sizes and measures, forest plot funnel, subgroup analysis, grade assessment, and that's it. So now, one of the things I need you to understand before we get going is that there are other things that I will still want to talk about. I've just kept this course very simple, particularly for those of them that are actually coming from the beginner's background, and essentially, some of the things you're going to hear from here is going to actually be very great in getting you started in the next phase. So if you're already very conversant with this, then you can actually get to our next video where we will be demonstrating a lot of practicals on how to write your meta-analysis. Now, whenever we talk about a meta-analysis, just think about the meta-analysis as we are trying to answer a question using numbers. That's a very good area to look at it. So we're trying to use statistical approach to address a question. So I'm not really going to talk so much about a bunch of chunks here. To get this slide is down there in my community. You can always check out on the community. I will do share, very useful slides that are quite important. And now, what is actually the root word for this word meta-analysis? Is that we're trying to just combine the results of several studies on the same topic, okay? To get more like a clearer picture of what we have intentions of doing. Now, you could be working with the research question of what's the effectiveness of maybe any type of drug, or maybe prevalence of maybe a certain health condition. Now, where meta-analysis comes inside now is that we're trying to now, instead of summarizing with one estimate, we need to now pull our findings from several prevalence studies, summarize it to actually get a pooled estimate where we can say, okay, this is our meta-analysis based on what we've regressed around a lot of studies. Now, that's actually a very kind way to explain that. But on the long run, when we start to practice, you're going to understand better what we're trying to do. So it helps in reducing uncertainty and provides more trustworthy evidence for clinical decision making. So if you look at the hierarchy and Beck evidence, you see that meta-analysis is at the top of that particular evidence. So it is really, really very important, aspect of research that provides a very sound result that we use in making reliable conclusion. Now the question might be, how does it now really differ from a systematic review? Is a meta-analysis, unlike a systematic review that collects, appraises, and summarizes studies from multiple studies, meta-analysis does likewise, but it goes a bit step further by using some kind of statistics to combine numbers and produce a single overall result. So don't worry. Everything I'm talking about is going to be very easy. You're going to watch out how I'm going to practice this and use real-time research questions to explain this, okay? So what we are saying is that if you're doing a systematic review and meta-analysis, for example, as a topic, it's possible that you might have 10 included studies as your systematic review to answer your systematic review question, and then you might have like maybe 5 that will lead to meta-analysis, okay? So it means that meta-analysis is this subset of a systematic review. It is that numerical part. It is more like a numerical method of analyzing data for what? A systematic review. So just think about a systematic review like a short story, while meta-analysis gives you the numerical verdict of that story. So yeah. Now, what actually some of the steps in performing a meta-analysis? Like I said, it's not different from how you do a systematic review in the traditional sense. You need to actually identify a question, probably what is the risk of maybe breast cancer among women. You want to try and get the pooled risk, right? Now that's a clear question. So you need to refine it to the model. The same thing you're going to do for a systematic review. You probably have to select the appropriate studies. And when you've selected the studies, then the next thing is for you to extract, data out of them. That is where we now start extracting those numerical data out of those studies, and then before we can now analyze it using our own choice of maybe meta-analysis approach. Okay, so it is not different. It is still the same approach that we use in doing systematic review, but the difference now comes particularly in the results, how the result is being presented. Okay, so yeah, that's just what it is. Now, what are actually some of the key tools for you to perform a meta-analysis? Now, for you to get started with the meta-analysis, there are a lot of softwares. So I'm going to actually advise you to install R, maybe, or Revman. Personally, I do prefer Revman. I use it's a Cochrane tool, and that's what I use for my meta-analysis. Some other people prefer using R or more conversant with Revman. And there are also other statistical softwares like Stata, CMA. So lots of them out there that can be very useful for you to perform your meta-analysis. So it's just like, think about it like a tool. It's just like in programming, maybe you want to write some kind of machine learning code. You might want to say, okay, I want to use Python, or I want to use R Studio, or whatever R software, or maybe R programming language to address the same question. But in this time of meta-analysis, you must install a statistical package that is going to help you in running your analysis. So yeah, this is the right video for you to watch. Remember, you need to like and subscribe now. But the question is, what are you going to learn in our practicals on the long run? Now, some of the things you might learn is you might get to learn how do you choose the right model. You need to understand what forest plots are, funnel plots, and how to show bias. And I'm going to be explaining all those things in this video. Don't worry, I'm going to explain it in details. And then you also understand how to perform, interpret, and explain, a full meta-analysis confidently. Okay. And also the grade assessment, which is something we're going to be explaining. Okay, so you need to make sure you pay attention and listen, and maybe you can always go back if there's anything you didn't understand. So you might make sure you understand the theories very, very well. So whenever you start jumping into interpreting data, everything is going to make sense for you. And the question is, why do we conduct meta-analysis? Okay, just like we said at the beginning, to get a clear answer. All right, so let's assume you want to do a drug-to-drug intervention or whatever. The result from a meta-analysis is very, very, very rigid in making, clinical conclusions, okay, and answering questions. It also helps us, it increases the confidence that we have, over any kind of estimates that we're trying to go through, understanding precise, random errors and all that. And also it helps us to identify patterns, okay. This is actually very important, particularly when you're working on data that is related to a certain distribution of, or maybe any kind of field, and there is very massive need for, maybe you're working with several factors. Now, meta-analysis is very imperative because it will now help us to streamline and know what we want to do. And like we said again, informing decision, it's still the same, because evidence from meta-analysis is what we use in making several clinical based recommendations. Okay. I'm just going to recap again for you to get what I'm saying and make sure you understand really well what I'm talking about. And that's that this is a statistical method for combining results from multiple studies addressing the same question. Remember that if you want to actually do a meta-analysis, take for example, you're trying to understand maybe the pool prevalence of malaria in a certain community. All the studies has to be addressing all the individual studies must be addressing prevalence of malaria. Okay, so that's what we mean by it must be addressing the same question. And another objective is that it increases power and precision. Don't forget, also get that's like you're trying to get the trials around exercise and blood pressure reduction. Okay. Now, in terms of the outcome, we have several outcomes that we're looking for. Maybe we might be looking for effects, maybe mean difference, risk ratio, standard mean difference, odds ratio, and a lot of them. Okay. At the end of the day, these are the outputs we use in making conclusions. Don't forget, we use evidence from a meta-analysis to make conclusions. So we must make sure we get very, very lovely with the analogies. And again, is combining multiple. For example, I just think about it like you're trying to combine multiple thermometer reading for a reliable temperature. So in that situation, that's what the meta-analysis seems like. Okay, so just picture it that we want to answer a broad question, but we need small studies that are numerical, okay, to address that question. Now, I wouldn't continue without pointing back to the hierarchy of evidence. And what's the implication of the hierarchy of evidence? The implication of the hierarchy of evidence is to call us back to that consciousness that where the meta-analysis evidence sits in the hierarchy, in the Pollitt and Beck evidence, of course, yeah, in the pyramid, or whatever thing you can call it. So if you look at this pyramid and you find out that meta-analysis and systematic review are sitting at the top. Okay, meta-analysis is sitting at the top. Because of what? Because of how rigorous conclusions are made. So we draw findings from other foundational studies to now summarize what is up. So take, for example, when you look at this now, you find out that if you want to conduct a meta-analysis of prevalence, people might want to pull evidence around case control or cross-sectional studies to address that. Or alternatively, you might pull from randomized trials to address that. So that is why it has to sit at the top, because it will now have to adjust for all the rigor that is in these primary studies to now come out with its overall estimate. Okay, so that's actually very, very reliable research one might want to perform. Now, it begins to get a bit tricky here, meaning that for you to be able to, remember that we just agreed that, okay, this is going to just be strictly on theory, okay? Now, in this case now, for us to be able to run any kind of statistical analysis and all that, there are certain effect measures we might want to take into account. And for you to perform a meta-analysis using any type of interface, you must always have it in mind for you to determine, okay, what is the risk of improving malaria or whatever, right? There are effect sizes for you to put into consideration, and that's what we call what? That's what we call effect models or sizes, right? That's why we have the odds ratio, risk ratio, mean difference, standard mean difference. So this is what determines the magnitude of the effect we want to perform in our meta-analysis. Don't forget, we're going to actually explain all this in details because we'll always refer back to this. And now also another statistical concept we put into consideration is what? Confidence interval. Whenever we want to perform a meta-analysis, whenever we're making conclusions, we look around our confidence intervals to know the range of the true effect. If it crosses one, or if its effect, if its effect is significant or not. Also, another thing we need to put into consideration is what we call the p-value. Okay, p-value is also very, very important. I'm going to show several examples in this session of forest plots that has all the statistical concepts that we are trying to talk about. And another thing is what weight. We put into weight. We take accountability of the weights because the larger studies are, the more influence it will have on the pooled results. So let's say, for example, a study that has a more higher sample size, there are more likelihood that it's going to have more effect on the overall result. Okay. Also, there's also another thing we call the heterogeneity, and what we refer to as heterogeneity is what? There are many times when we want to perform a study. Let's say, for example, prevalence of whatever, malaria, and now this study is measuring prevalence using another yardstick. Maybe the other one is measuring with another yardstick. These are heterogeneity, and now we could be also doing an effect of intervention study where we are working with several randomized trials, and there are several yardsticks for these studies measuring the intervention. These are variations. So in meta-analysis, we use what we call the I-squares to measure the what? The heterogeneity. That's what we're using testing for heterogeneity. We're going to explain it further in the course of this session. Now, I'm just going to actually go slightly deeper into effect sizes because I did mention effect sizes as how, some of those, if you look at here, we talk about how we quantify the magnitude of an effect. But here, it's still the same thing, but we're just trying to say deeper that, okay, we want to measure how strong or large is the effect of an intervention. Okay, take for example, comparing placebo and the kind of drug. In this range now, we're trying to know how large. Okay, which particular measure do we want to use? I want to use risk ratio, because risk ratio now is going to tell us, okay, there is high risk or there is low risk, and so forth and so forth. Okay, so for confidence interval, the range where the true value likely lies. So just like saying, oh, my friend, what's the height of your friend? Say my friend is between the range of 80 to 90. So that is the what confidence interval. All right, so that's it. And yeah, so we actually look at p-value. Usually whenever p-value is less than 0.05, we say it is what statistically significant. And then if it is equal to 0.05 or greater, we say that it is what not statistically significant. So these are several times we're going to be playing around. Remember the weights, I talked about it, about larger studies and heterogeneity as well. How we do measure variations between the studies. So I'm just going to give you a kind of an example to make that sink in very well. For you to talk about effect measure, effect size, odds ratio, we use it several whenever we are exploring binary outcomes. What are binary outcomes? Okay, yes and no, a type of outcomes and all that. More like categorical binary outcomes. So let's say, for example, what are the odds that smokers develop of smokers developing lung cancer versus maybe non-smokers? Okay, so here the interpretation is based on OR, odds ratio. So now same thing applies for risk ratio. We use binary outcome, but mostly for risk. Okay, what is the risk of heart disease in those on the Mediterranean diet? And then we've got another very magnificent effect size, which we call the mean difference, right? Where we try to understand the continuous. We use it usually for continuous outcomes. Okay, let's say for example, we want to understand maybe the average drop in blood pressure after a drug treatment. In that situation, now our mean difference is going to be what? It's going to be very important for us to perform or calculate the effect, the quantify any certain what meta-analysis. And we also have the standard mean difference, which is still like the continuous outcomes, but now is whenever we're using different scales, we'll convert it to a standard unit and then use it to make our assessment. We also have other effect sizes like correlation, where we try to understand strength, use a correlation between exercise frequency and BMI and all that. So there are lots of effect sizes too that we might not have talked about. Now, I just had a refresh now of this again. For you to conduct a meta-analysis, you get a question. Usually, it could be PICO, PO, whatever one that is suitable. And then you need to conduct a systematic search. Someone will do a systematic review. And then you need to select studies using an inclusion and exclusion criteria. And then you've got to extract data and code out of the studies that you've included. Then we'll have to assess the risk of bias of the studies. Then that is where after that we'll now perform our meta-analysis using either any two, either F1 or R, and then we'll now report it using the Prisma flow diagram. Okay, so these are some of the things we need to understand. So I did mention Prisma guidelines, okay, or any other established guideline for reporting the meta-analysis that you've got. Now we talked about effect sizes, right? Particularly how do you want to quantify the magnitude of effect or magnitude of whatever in his study. Now there are still what we call fixed statistical models, and now these are like try to look at it as the homogeneity or heterogeneity of your study determines that. So if you are working with a study that has similarities among all of them, then a fixed effect model is going to actually be applicable. Remember, it doesn't really affect so much of your data or of your probably your results, but it's also very important because if there are actually slight changes, then it's definitely going to show massive accounts for that. And I've got the random effect measures whenever you're working with studies that have different effects, maybe different population, different lots of stuff. Okay, so that's actually very good statistical model to use. Ensure that I do suggest that even when you don't even know the one to use, it is very important for you to use the word random effect measure. So before ever you start the work, you need to actually check for homogeneity, which we mean trying to explain as if there are some kind of similarities or whatever between the studies. It assumes all included studies are estimated with true effect. Okay, that's the fixed now. Another one, so it's saying that differences in the studies are believed to be due to random sampling error rather than differences. Okay, so these are quite important for you to take account into. And usually the pooled estimates represent the single best estimate of the treatment effect across all the studies because of what that similarity that they have. And on the contrary, other things we need to check out for, we need to be sure that that the random effect model adds an extra layer of variability called between study variance. And also, let's take for example now, we want to do a meta-analysis of exercise interventions across different countries or maybe across different age groups. Now we have to use a random effect model because of there are differences in these settings. Okay, so yeah. So when do we use each of them? It's already explained. First of all, we use a fixed effect whenever there is similarity, right? Whereas for the random effect when there is no similarity. And now one thing I want you to understand is that for the heterogeneity, remember we talked about I squared as heterogeneity. What it means is that there is always a cutoff point for it where we can say that okay, there is similarities among these studies, and you get all these figures when you have performed your meta-analysis. Do you understand? Particularly the I squared data. So don't worry, just make sure you understand everything I'm talking about, and that's the most important thing right now. So now we talk about heterogeneity. Now what's heterogeneity? Now heterogeneity means differences of variability in results across the studies included in the meta-analysis. So more like differences of variability in the studies or in the results included in the meta-analysis. So let's take for example right now, we want to say, imagine you ask 10 doctors about how effective a new hypertension drug is. So if all of them give similar improvement percentages, that's low heterogeneity. But if there are varying inputs, then that's what? High heterogeneity. So how do we measure heterogeneity? First of all, we can measure it using the Cochrane's Q test. We can use the I squared test statistic, which is usually cut off at, most times we say once it's less than 50, then that means there is significant heterogeneity. Once it's above 50, there is what? High heterogeneity. If it's low, there is low heterogeneity. If it's high, there is high heterogeneity. We also have the tau squared, where we usually use it to compare the true effect or understand the variance of the true effects sizes between some of the included studies. And we have the interpretation, where we usually highlight it as I, means that I squared means whatever thing you're reporting in your results. I'm definitely going to show that in the next video. You will get to understand that better. And let's say your I squared is 50, then that means it's very heterogeneous. If your I squared is less than 50, then that means it is maybe homogeneity is worrying it. Okay, yeah. And now the next one is the Cochrane's Q test. Okay, this is all wrapped around Revman. It's a statistical test that checks whether the variation among the study results is greater than what would expect by chance. Okay, so that's always very important whenever you have any sensitive data. Variability is not just the problem. Okay, but what studies differ genuinely. So the Cochrane's test now will help us go more deep and now know between our studies are there quite some maybe some kind of homogeneity or heterogeneity or similarities or differences that can be observed. Okay, and before it will now prompt the use of random effect meta-analysis model. Now the I-squared test. Now this is how it's rated. From 0 to 25 is low heterogeneity. From 25 to 60, moderate heterogeneity. From 51 to 75 is what? Substantial heterogeneity. Greater than 75 is what? High heterogeneity. So that's what I-squared is all about. So whenever you plot your forest law and you find this out there, you need to know how to interpret it and get very clear with that. So the tau squared is, it represents the actual variance in true effects. Okay, another one was to get the differences in the variance. So here we want to get the variance, and want to use it to quantify the amount of heterogeneity. Not just percentage. All right. So let's take, for example, I want to say, okay, how much do the true effects actually differ from one another? And in meta-analysis of 10 studies on anxiety, that shows that, okay, if tau squared is 0.15, then there is mild, or I can actually say moderate variance in the effect sizes. So there are a lot of reasons for you to do a measure heterogeneity. One of several reasons why it matters, and because you want to know the type of model which you to use, the random effect, and it affects how confidently you can generalize findings. Okay. And because if there is heterogeneity, because we do have that, when people submit papers and there are lots of related papers and all that, or maybe somebody publishes a conflict and all that. So this is what actually addresses that particular aspect. And if your meta-analysis, let's say for example, you're working on an antidepressant and it shows 70%, then explore why that happened. You may even, it depends on whatever, because if there is massive gap, then there is a challenge. So I'm going to repeat this again. 0 to 25 is low heterogeneity, 25 to 60 is moderate, then greater than 75 is what? High, and 55 to 75 is what? Substantial. Now we're going to talk about some of the forest plot interpretation, which is a very crucial part of meta-analysis, because now we've talked about some of the effect sizes, we've talked about effect measures, we've now started with the tool, but there are some certain things we need to understand, which is what? The forest plot interpretation. Now, each line on the forest plot, I'm just going to show you what that looks like. You can have a look at this. This is the lines now that I'm talking about. You see that each line, it shows one study. That's for each line is one study. Then the square that you find there. I'm just going to check out that. That's for this. Studies weight. It shows the studies weight, right? We're going to check out the examples. And then the horizontal line, usually the 95% confidence interval. Do you understand? And then the diamond is the pooled estimate. Just like this. So let me just show you this. Now this is the diamond, the pooled estimate. This is the confidence interval. Okay, this is the confidence notes from here to here and all that. Okay, we also have another one. We've got this. This is what? You can see the lines and the confidence interval and all that. Now I'm also going to actually more like put in some kind of explanations again to the forest plot. First of all, just like I said, each line represents one study, and the square represents the study's weight. Okay, so that's what the meter squared does. And what else would you want to know? You want to also know that the horizontal line through each line is the confidence interval. Okay, so if you look at those lines, that shows you what confidence interval. Now also, if you also check out at the bottom, you see the diamond there, right? So it's usually at the center, and what it does is that this is what that actually pulls the overall estimate, right? It is like the width of a diamond. So this is what it looks like. This, and also you can actually check out this. See how big it is. Probably because I compressed it or something. So this line is actually very, very important when we're going to be doing analysis. We're going to be explaining what this result is like, and that's quite a lot of things we're going to explain. Now, I usually explain this. So I'm going to also show us how to read the visuals of a forest plot here. Now, whenever we talk about funnel plot, the first thing that comes to our mind is what? Publication bias. So we want to know if there is publication bias. Whenever we're talking about a funnel plot, we want to know why did you not, or probably we can say why were some articles excluded and all that. So a lot of researchers are found to this. So we'll plot the publication bias score, which is the funnel plot. Then we'll now try to know if, according to the Eggers test, if there are some certain studies that we are omitting on, or maybe we're actually going for the ones that favor it. So make sure you register your work on Prospero. It's also a very good ethical practice for you to perform any type of review. It's always very important for you to start by registering it. When you register it, everything essentially makes massive sense. So yeah, I'm just going to talk about this more further, and I'm going to say, okay, yeah, if funnel plot just helps you to detect bias when studies with positive or certain results are more likely to be published than than that of maybe negative or non-studies. So just think about it as I want to know: are you just only going for one type of studies that is bias, right? Or are you going for are there some kind of heterogeneity in your studies for us to now assess the publication what bias? So this is just what everything we've talked about right here. This is what it entails. So now there are two types of funnels. We've got a symmetric funnel and asymmetric funnel. So what the symmetric funnel shows is that it shows us that that the studies are evenly spread, on both sides. So let's go back to this chart here now. If you look at this now, you find out that here, let's assume that we just did a meta-analysis of a particular outcome or evidence now. So if we look at this side and also look at this side, we'll find out that what here now there is unequal distribution with this one. Look at where this one is, look at where this other one is, look at where this other one is. So it shows that it's what is balanced, is symmetrical. Do you understand? The tasks are trying to make sure they join themselves and all that. That's some of these dots rather. So that's why studies are evenly spread on both sides for a symmetric funnel, and then for an asymmetric funnel, there is mixed studies on one side, and possible publication bias, which means that some studies were not published. So remember, I did mention it clearly here. Symmetry means good balance. Asymmetry means what? There's a potential, okay? And yeah, that's probably some of your studies, all of them are all the same design. Maybe there is so much rigor and cool and all that, but then it doesn't really show. Maybe there is publication bias, probably depending on the reason. Oh, everybody has money here. Maybe that's just it. For example, let's say, for example, then instead of you to also consider other people that don't have money, it's just only people that have money, and that brings bias. So the idea of systematic review is to kind of spread out, so we can have quality evidence. But all the same, yeah, I'm not trying to question the quality of whatever work maybe that turns out to show maybe low publication bias, or maybe that is that is asymmetric or whatever. But these are some of the things we need to always put into consideration, while making our judgment and all that. And also the method to detect bias here now, it shows that for a meta-analysis, you can use visual inspection, which is what we do. We look at the funnel plot and we use the Eggers regression test, which is another way to calculate what the funnel plot and understand the publication bias. So there are a lot of ways to prevent it by registering your review protocols early, to reduce people that are going to challenge you really well, and then to search good literature, and also to include eligible studies, and encourage open access publication. These things are quite very important whenever you're submitting and you're making claims about this. So publications can inflate effect sizes. A lot of things can actually happen. Detection and addressing it's also something that improves the credibility and transparency of your meta-analysis. And again, is that clinicians can then trust that results reflect our available evidence. Now, I just tried to show you some of the difference between symmetrical and asymmetrical. And this is also something that comes close to what I was trying to talk about, okay? Now, we're going to talk about subgroup analysis and sensitivity analysis. Don't worry, we are progressing really well. Now, whenever we talk about subgroup analysis, now think about it this way. That you want to actually perform a research, and then, let's say, for example, it's a research on malaria. Now, when I want to do maybe malaria among maybe women or whatever in a certain community and all that, when I want to do subgroup analysis, what it implies is that I might now maybe under those women now do a subgroup analysis of certain age. So what subgroup analysis does is that it gives us more clearer picture of the evidence that we are trying to address. And then for sensitivity, sometimes you could actually pull up your evidence. Let's say, for example, this. And then at the end of the day, you now look at, I think I want to remove this larger study with highest weight. Let me remove it. You remove it, and maybe remove this other one, 2020. Then you now run a subgroup analysis based on maybe either two on a certain terminology that you guys have, and that's it. So essentially, so now the next thing we might have to look at now is some key terms that are relevant to subgroup analysis. Remember, guys, you must make sure you join Sentinel Research community and get all these massive updates there. In this subgroup analysis now, some of the idea behind doing a subgroup analysis for us to also understand much more detailed information in specific groups that are in the population group that we're working with, or maybe the studies that we've chosen. So these are all very good prerequisites, for you to perform, other type of analysis apart from the systematic review. You can also do sensitivity analysis where you remove the biggest from the lowest, all right? And also you can do a maybe cumulative meta-analysis, leave one analysis, and all that, several of them. Yes, so this is where a lot of people get confused when we talk about the grad assessment. Now, what is the grad assessment? It's just like a structured way of judging how strong or trustworthy the evidence from a meta-analysis or systematic review is. So even whenever you finish an article, right, you still need to make sure you get all these things sorted out immediately. Do you understand? That's what we call it, the grad assessment. So yeah, it is usually used by WHO and World Health Organizations to answer clinical questions. So now, before we go ahead, now we need to understand what are the domains of the grad assessment. First of all, we have 5 domains: risk of bias, inconsistency, imprecision, and indirectness, and publication bias. We already talked about publication bias, which is from asset test and EGAS test rather. And now for risk of bias, it is the main one that we're going to be working on. So where we can actually make comments. Inconsistency on the other hand is where we can check out. And then for imprecision, we look at data, right? That's like I want to know how much do this data vary from different studies, and it's just very, very close here. So the levels of grading that's how we use grad assessment is first of all, the first thing we will usually do now is we have high, moderate, low, very low. And now whenever somebody says, oh, we are very confident on that car, then that's maybe I use a car, that's very, very, very high. So this you can also apply to your research, try and run it. Probably when we are doing practicals, you get to see how all these things works, and then you play with it around and all that. Yeah, so when reporting it now, we're going to report it based on numbers. We can say, okay, high, low, then we make comments and all that. This is actually very, very important for you to do a systematic review and meta analysis. So yeah, that's that. So now, some of the things we need to find in these reviews is that first of all, it's actually going down, downgrading, or upgrading. That's just it. So that's for the grad evidence. Now, if you want to talk about risk of bias, now 2 studies had unclear findings, for example. This is risk. Maybe you can say downgrading, because blinding is a very, very crucial part. And then in terms of inconsistency, you can say the I squared is 70%, that's varied result. So the conclusion from this study is it's going to vary. Then same intervention, we've got maybe sometimes we want to make comments about the maybe an intervention of a particular meta-analysis. So we have to comment and be sure that maybe it goes in line and is consistent. Then indirectness is same intervention but different direction. Final written, it's now where you now get all these things together, as well as your publication bias as well being accounted for. So this is how you're definitely going to present it. You've got high, you talk about, you put a comment, moderate still, you put a comment. So this is where it gets all interesting. Guys, thank you for staying. Remember to like, share, and subscribe, because it's going to be powerful with practicals. I'm going to tweak a lot of things, try and get so many things done. And some of the common mistakes people make is they mix different effect sizes, they ignore heterogeneity, misreading, skipping bias assessment, reporting only the ones they want and all that. Lots of problems. Another one is you need to follow the Prisma item. Okay, and it's quite very important. There are actually a lot of things, 7 items there. The Prisma item. So comparing your studies has to still follow the same way as a systematic review. You need to compare with prior research. Consistency or contradiction is not allowed, and you need to discuss practical implications. With maybe the right tool and the right assessment and all that. So guys, like I said, we're going to be starting practicals as soon as possible, and that's going to actually give us an edge to sink in all this in. Because guys, remember, if you want to actually get my focus on how to conduct a meta-analysis, this is it to get started. And I'm going to be increasing the price next week, so make sure you keep in touch with it. Thank you so much for your time, and yeah, it was quite a pleasure to have you. Thank you.